Welcome. This video is going to talk about molecular formulas and how you can determine the molecular formula once you know what the empirical formula of a substance is. The molecular formula may or may not be the same as the empirical formula, but it will be a whole number multiple of it. So either the same, so a multiple of 1, or 2, 3, 4, etc. You need to know two things in order to calculate the molecular formula. You need to know the experimental molar mass, and for most of our problems this will be given to you, but if you were actually in a laboratory you would measure this or calculate it. And then you need to know the calculated or theoretical molar mass of the empirical formulas. So you've determined the empirical formula or the simplest ratio, and you go ahead and plug in the atomic masses for those elements and calculate a molar mass for the empirical formula as if it were your molar mass of your molecular formula. So take a look at an example. An unknown substance is found to have an empirical formula of N2O3. So that means the molecular formula could also be N2O3, or it could be some multiple of this, such as N4O6 or N6O9, etc. The experimental molar mass has been found out to be 2.281 grams per mole, and they're asking what is the actual molecular formula for this compound. So the process is actually quite simple. I go ahead and take 2 times the known atomic mass of nitrogen, and I add it to 3 times the known atomic mass of oxygen. So just like you normally calculate molar mass for a known compound, in this case I'm just doing it for my empirical formula. And when I take 2 times 14.01 plus the 3 times 16, I'm coming up with an empirical formula's molar mass to be 76.01. The experimental molar mass has been found to be 228.1, which is quite a bit more. So that means that the actual molecular formula is bigger than just N2O3. But it has to be some multiple of this, so I just need to compare the two masses. Take the 228.1 and divide by the 76.01. And the experimental should always be the greater of the two. If they're not equal, then the experimental molar mass should be the one that's bigger. And I take 228.1 and divide by the 76.01, I come up with 3.0009. So basically 3 times the mass of what the empirical formula has. So that tells me I need to triple the empirical formula, and my actual molecular formula must be N6O9. So here's another example. An analysis of a chemical used in photographic developing fluid indicates a chemical composition of 65.45% carbon, 5.45% hydrogen, and 29.09% oxygen. The molar mass is found to be 110.0 grams per mole. Determine the molecular formula. Well, it doesn't expressly tell me in this problem that I need empirical formula first, but if you remember, the two pieces of information you need to find molecular formula are the molar mass of your empirical formula and the experimental molar mass. So I'm going to have to find the empirical formula so I can calculate an empirical molar mass. So remember, when you have percents, you can just change them all to grams, assume it's a 100-gram sample. So I can take my 65.45 grams of carbon. I need to change it to moles. This goes back to our empirical formula lesson. I know there's 12.01 grams per mole for carbon. So this means I have 5.4496 or 5.450 moles of carbon. The 5.45 grams of hydrogen, my conversion factor is 1 mole over just 1.01 grams per mole. So I'm going to have a little over 5.396 moles of hydrogen. And then my 29 grams of oxygen, the conversion of 1 mole weighs 16 grams for oxygen. So 29 divided by 16 gives me 1.81, I'm sorry, 1.813. So then to come up with my empirical formula, I would have C 5.450, N 5.396, I'm sorry, that's H 5.396, and my N is, or my O is 1.813. And now I have to divide them all by that 1.813. Sorry, things are getting a little crowded here. 813 and divide by 1.813. And when I do this, the 5.45 divided by 1.813 is 3.006, or I can round that to 3. The H, 5.396, is going to be even closer to 3, 1.813. 2.976, so again I can round that to 3, and the O would be just 1. So there's my empirical formula. So now I can actually start working on what I was interested in, which is the molecular formula. So C3H3O is my empirical formula, and that would have a molar mass of 3 times 12.01 plus 3 times 1.01 plus 1 times 16. And when I calculate that, that gives me a molar mass of 55.06. And again, this is less than the molar mass found for the actual compound. So I compare the two by taking the 110.0 divided by the 55.06, and you can probably tell it's going to be very close to 2. And in fact, it is 1.9978, or twice as much. So then I know that my empirical formula needs to be doubled. So I take 2 times the C3H3O, and it becomes C6H6O2 for my molecular formula. So here's one for you to try. The empirical formula for both acetylene and benzene is CH. Find the molecular formula for each if the experimental molar mass of acetylene is 26.04 and the experimental molar mass of benzene is 78.12. So if you want, go ahead and pause it here and see what you come up with for a solution. So my first step would be to find the molar mass of CH, or the empirical formula. So 12.01 plus 1.01 gives me an experimental molar mass of 13.02. So for the acetylene, I can take 26.04 and divide by the 13.02, and I see that it's 2 times as much, or acetylene must be C2H2. Whereas benzene is 78.12. So if I take that and divide by the 26.04, that tells me it weighs 3 times as much as the empirical formula. So benzene must have a molecular formula of C3H3. Here's another one for you to try. Succinic acid is a substance produced by lichens. Chemical analysis indicates it's composed of 40.68% carbon, 5.08% hydrogen, and 54.24% oxygen, and has an experimental molar mass of 118. Determine the molecular formula. And again, you're going to need to find the empirical formula first. So go ahead and pause and see what you can do on this problem. But your starting point would be the 40.68 grams of carbon can be converted because 1 mole of carbon weighs 12.01. So 40.68 divided by 12.01 is 3.387 moles of carbon. The hydrogen you have 5.08 grams, and 1 mole of hydrogen weighs just 1.01 grams. So it's going to be very close to 5. 5.030 moles of hydrogen. And then my oxygen at 54.24% or grams can be converted with 1 mole weighing 16 grams. So a little less than 4, 3.39 moles. So now when I set up my empirical formula, C 3.387, H 5.030, and O 3.39. So I'm basically dividing these each by 3.39, or 3.387 if you prefer. But the C and the O are going to both become 1, and the H, 5.03 divided by 3.39, gives me a fraction of 1.484, or approximately 1.5. So if you remember back to empirical formulas, we can't keep that fraction in there. So my empirical formula is actually C2H3O2. And so now I use that empirical formula to calculate a molar mass to compare to that 118.1. So I've got C2H3O2, which would be 2 carbon at 12.01, 3 hydrogen at 1.01, and 2 oxygen at 16 grams apiece. So the molar mass of my empirical formula the 2 times 12.01, the 3 times 1.01, plus the 2 times 16 gives me a mass of 59.05. And when compared to the 118.1, I see that my experimental molar mass is twice as much, so this gets doubled yet again and becomes C4H6O4 is the molecular formula.